Welcome everyone to today's video about photochemistry and the kinetics of it. So in this video we're going to talk about photochemistry. Now a little bit later on we'll talk more specifically about electronic absorption, rotational, vibrational absorption, and that type of spectroscopy, and on kind of the quantum mechanical level and the energy levels and the energy required to do these things, and all sorts of other wonderful stuff, right? But we'll for now not worry about that. Just understand the idea that the electronic states and vibrational states and rotational states in atoms and molecules are quantized. There are certain energy levels that exist, and you can go up and down in these energy levels if, say, you excite the molecule with light, right? Light has some amount of energy, absorbs that light, takes the energy, goes up to a higher energy level, right? And once it goes up to that higher energy level, it's going to go back down, okay, right? Things want to go back to the lowest energy, right? That's kind of their equilibrium, their thermodynamically favorable state is the lowest energy state, right? So things want to go back down. And so today we're going to talk about kind of the kinetics of those things returning back to the ground state. So before we get there, we'll just briefly talk a little bit about singlet versus triplet electronic states. Okay, so if you recall right from general chemistry, right, you have your like m sub s quantum number, right, which is plus or minus 1/2, which has to do with an electron having like an up or say a down spin. Okay. Right, in each orbital, you can have at most 2 electrons, right? If they're in the same orbital, one's going to have an up spin, one's going to have a down spin, right? They're going to be paired together, okay? That pairing, that pairing, if you have an even number of electrons, okay, will produce a molecule that has an overall singlet electronic state, okay? So this notation here, right, I have an electron 1 with spin up, electron 2 spin down, and they're occupying some orbital energy here, right? Say your highest occupied molecular orbital, right? Okay, and so an occupation of electrons like this produces again what's called a singlet state, singlet electronic state. Okay, and it's called a singlet state because it's singly degenerate. There's only one way your electrons can fill up the orbitals like this, right? And that's it, right? What's shown is how you can do it, okay? Well, there are other ways if you have your electrons split in different orbitals where they have the same spin, for example, right? Or maybe some combination of opposite spins like what's shown here, right? Where all 3 of these states end up having the same energy, okay? They have the same energy, so they're all degenerate, okay? Talked about this semester and last semester a little bit about degeneracy, right? Degeneracy means same energy, right? So these 3 ways of occupying your electrons, and say, your HOMO and your LUMO level, highest occupied molecular orbital, lowest unoccupied molecular orbital, right? Right. These different ways you can occupy these orbitals, right, all produce the same energy, and so this is triply degenerate. So these are called triplet states, okay? And note that typically for a triplet state, you have the 2 electrons that we're interested in have the same spin, okay? Right, so the singlet state, they have opposite spin, triplet state, they'll have the same spin, okay? And so transitioning between these states can be difficult for atoms or molecules unless you have heavy atoms, okay? Your heavy transition metals or actinides or things like that, right? Heavier elements are able to flip these spins easily, but typical, say, organic molecules can't do so, okay? And so typically ground states for most molecules, especially organic-based molecules, the ground state is singlet. And so when you photoexcite the molecule, it stays into a singlet because it's difficult to flip that spin to go from a singlet to a triplet state. So typically you'll go from a singlet to a singlet in your excited state. And then once you've formed that photoexcited singlet state, then that thing can decay back to the ground state in a variety of ways. And so we'll discuss that now. So the type of processes that can occur in photochemistry, right? There's a bunch given on this table on the right, okay? just highlight, right, you know, your absorption, okay, and then you have fluorescence, right, which is basically the opposite of absorption, right? Absorption, you absorb the light. Fluorescence, you emit that light, okay? Stimulated emission is basically using light to help the molecule emit the light that it can, right? Things like intersystem crossing, where you go from a singlet state to a triplet state, okay? That can be a very slow and unlikely process in a lot of organic molecules, okay? Phosphorescence is what it's called when a triplet state emits, okay? So glow-in-the-dark material, right, it typically undergoes phosphorescence because that triplet states exist for a much longer time because it's difficult for them to transition back to the singlet. So it takes a long time for that to occur, and so that's why glow-in-the-dark materials last for a while, right? You kind of charge it up in light, and then they'll last for a while and glow for a while in the dark after that, because of just the lifetime, how long it takes for that triplet to get back down to the singlet ground state. And that process is phosphorescence. Okay. There's something called internal conversion, where basically you go back down to the ground state without emitting any light. Okay. Typically the energy just goes into vibrational energy and rotational energy and things like that, kind of heats up your system. Okay. And then there's some other processes down here that involve multiple molecules, okay? We're not going to worry about these, okay? So this stuff kind of down here involves two molecules colliding, interactions between two different molecules, and other things like that. And so we won't worry about any of that stuff, right? And we're just mainly going to focus on the idea of intersystem crossing, fluorescence, internal conversion, and phosphorescence, okay? So in photochemistry, we'll often talk about quantum yields, about yields of certain states, right? So quantum yield is like any yield, right? In your general, organic chemistry, when we talk about the yield of some product, right? It's kind of how much of that product did you get out versus how much starting material did you have, right? And so it's the same thing for quantum yield. It's the number of desired events you want, right? Versus the number of events that happened, right? So the starting material is the number of photons absorbed, right? And then, the amount of light that's been absorbed, that's their starting. And then the final is say, the number of light that got emitted, right? Or the number of triplet states that got formed, or things like that, okay? Right, well, if we think about the number of these events, right, you can relate the number of events based off of the rate of those events times the time interval that you're measuring things on, right? So if I am absorbing light, 1 absorption per second, right? If I wait 10 seconds, I have 10 absorption events, right? So I can relate my number of absorption events and a number of emission events based off of the rate of those things times the time interval, right? And since we're measuring kind of the same time interval, okay, this quantum yield is just basically related with the rate of emission versus the rate of absorption. Okay, so I abs here. This is your absorption rate, right? And VI here is your emission rate, right? And we'll talk more about what that is in the next slide. Okay. So there's different types of decays, again, that affect the rate of change of that single excited state, right? So you have the absorption, right? This is creating S star, right? S star is your photoexcited state, okay? So you have a bunch of absorption events, that create that photoexcited state, and then that photoexcited state can undergo different processes to get rid of itself, right? To kind of decay, if you will. The three we'll focus on are, again, emission, internal conversion, and intersystem crossing, right? So emission is just, it goes back down to the ground state by emitting light. Internal conversion is it goes back down to the ground state by, emitting energy through vibrational energy and things like that. Or intersystem crossing is it goes to a triplet state, right? And the rate of each of these things, right, these are kind of elementary steps, right? So the rate laws for each of these things, since they're just first order, they just depend on the concentration of that star, right? It's just the rate constant of fluorescence times the concentration of that excited state, right? The rate constant internal conversion, rate constant of intersystem crossing, right? So the overall rate of disappearance of that single excited state, right? Assuming, right, we've absorbed some amount of energy, we start off initially with some initial S star naught, right? Some initial concentration of the excited state, okay? And what is that rate of disappearance from there, right? Is just given by this equation here, right? Okay. It's just the sum of all these first order processes, which basically means you can just add up those rate constants, right? And so that gives you just a first order kinetics problem, right, where we have this integrated rate law, right, that's, you know, the concentration of that single excited state is related with its initial concentration times e to the minus t divided by tau naught, right, where tau naught is just 1 over the sum of these rate constants. Okay, so this is referred to as the lifetime. Okay, we often use this in photochemistry to talk about lifetime. It's 1 over the sum of the rate constants. Okay, right, the form we're used to seeing here, right, you know, Kr times T, right, where Kr is the effective rate constant of the reaction, right? Kr in this case is Kf plus Kic plus IC plus Kisc, right? Right, the effective rate constant is the sum of those rate constants, okay? Right, and so it's very simple, kind of familiar kinetics and things like that, right? So often when you talk, when in a paper, when you read about the lifetime of an excited state, right, that lifetime again is determined by the rate constants of these different processes, right? This fluorescence, intersystem crossing, and internal conversion steps, right? And sometimes some of these might be more dominant than the other, right? Let's say, right, you know, the molecule essentially has 100% quantum yield for its fluorescence, right? Then that means Kf is much, much greater than Kic and Kisc, right? And so the lifetime is mainly determined by, say, the fluorescence lifetime, right? But it could be, it's a combination of these things, right? If these are similar order of magnitudes, right, then the lifetime of the molecule is related with the lifetime of fluorescence intersection crossing, right? So for example, the lifetime of fluorescence is just given by 1 over Kf, right? And you can do the same thing for Kic and Kisc, right? And so you can relate 1 over tau equals 1 over tau f plus 1 over tau Ic and plus 1 over tau Isc, right? So you can also relate the lifetimes based off these specific events versus the total lifetime of your molecule, kind of getting these relationships and things like that, right? And these are very common things discussed about when talking about photochemistry. Okay? Now, let's talk a little bit more about how we can calculate these quantum yields and things like that. Typically, these are obtained using steady state experiments where you're constantly illuminating your system. And when you do that, right, so the change in concentration of this excited state is given by the decay process that we talked about already, plus then this is this absorption rate. Again, this I absorption is the absorption rate. Okay, that's your absorption rate. Okay, right. And so if we have constant illumination, right, we'll reach a point where we're at some sort of steady state and the concentration of S is not changing over time. So ds dt, right, ds star is equal to 0, right? And so using that, right, we get the absorption rate just has to equal the concentration of the excited state times the sum of these rate constants, okay? And then if we go back to what we discussed earlier, right, where the fluorescence quantum yield, right, so the fluorescence quantum yield, again, is how many fluorescence events do you get over the total number of absorption events, right? So what, you know, your molecule, you have 100 excited state molecules. Out of those 100, what percentage is going to emit light versus do something else, right? That's your fluorescence quantum yield, right? And so again, that's given by the rate of fluorescence over the absorption rate. Well, we using kind of the steady state approximation, right? We have what this absorption rate is in terms of the concentration of that excited state, right? And the fluorescence rate, by definition, is just Kf S star, right? And so we plug in this for the absorption, plug in that for VF, right, to get this equation here. The S stars cancel, right, and you're left with this quantum yield, right? Which again, if we recall, in class we did an example where we looked at the quantum yield of two competing first order reactions, right? And we said, well, the final yield of the reaction we care about is just the rate constant of the reaction we care about divided by the sum of all the other rate constants, right? And so this same thing appears here. Because we have just a bunch of first order competing reactions, the quantum yield, right, for some event is just the rate constant of that event divided by the sum of all the other rate constants, okay? And again, this only works, and this holds true, because we have a bunch of first order, parallel events, right? If these were second order events and other things like that, then it wouldn't look so nice and easy as this, but because it's first order, it does, okay? Right, and so the last thing we'll talk about with photochemistry is what's called quenching, which is a very common experiment that's done, okay? So quenching is a process where you essentially remove the excited state energy from a molecule by introducing another molecule. You introduce some other molecule that when your original molecule gets excited, the energy from that molecule quickly transfers over to this other molecule, this quencher, okay? So again, a quencher, when added to your system, when you have some photoexcited state, forms, makes that photoexcited state go back to the ground state, and the quencher does whatever. Maybe it's photoexcited, maybe it's whatever, we don't really care, right? The main point is that this quencher is another way in which the single excited state energy is lost, right? Right, this ds star dt, now based off of this, right, is just related with minus that bq, which is minus kq s star q, right? And so, right, adding this quenching experiment, if you will, right, this quenching step to the other steps that we already had, right, with fluorescence, internal conversion, intersystem crossing, right, what you'll get is that this quencher modifies your fluorescence yield, say, in your lifetime by just adding in to that sum of rate constants, right? Just adding in those sum of rate constants, okay? Now, in this case, right, the effective quenching rate constant, right, the effective rate constant for the quencher is kq times the concentration of q, right? So often what's done in these experiments, and we'll talk about that in a second with these what are called Stern-Volmer plots, right, is you'll modify the concentration of your quencher for different experiments in order to kind of get out what kq is and some other things, okay? And these quenching studies are used all the time. Long ago, and maybe still nowadays in some situations, right? These quenching studies can be used to study the size and distances between certain regions in a protein, right? Let's say you know the sequence of your protein, but you have no idea, is this part of the sequence near that part of the sequence, in the actual folded protein, okay? And you can use some of these quenching studies to help determine that distance dependence, okay? So there's some really interesting stuff in interesting chemistry you can do with these quenching studies, and they're performed all the time still nowadays. Okay. So the Stern-Volmer equation basically uses what is your fluorescence quantum yield with the quencher versus without, okay? And if we take this ratio of the fluorescence quantum yield with and without the quencher, okay, right, these things cancel and you're left with a bunch of stuff here. Okay? Well, that term here, okay, we can break this up in the numerator, right, into kind of this section plus this section, right? And then this section is just equal to 1, and then this, right, is its own thing, okay, right, where, remove that one, right, where we see here that, right, this term here, 1 over kf plus KIC plus KIC is just the definition of the lifetime of that state without the quencher, right? So tau naught, right, again, tau naught is the lifetime, without the quencher, right? And so you can change the concentration of your quencher, right? and measure what the change in the fluorescence yield is with and without the quencher. And when you make a plot of phi f divided by phi f q versus q, the concentration of the quencher, right, you'll get a straight line, right? Y-intercept is equal to 1, and then the slope is given by tau kq, right? Which if you can measure outside of this experiment, right, you can measure what the lifetime is without the quencher, right? That's an easy experiment to run. And so if you have that, then you can use this Stern-Volmer plot to get what the quenching rate constant is, okay? Now there's another form of this Stern-Volmer plot, okay, that you can use in terms of lifetimes, okay? So we use kind of, again, definitions of lifetimes. Tau naught is without the quencher, tau is with the quencher, okay? And when you do that, you can rewrite this Stern-Volmer equation as 1 over the lifetime equals 1 over the lifetime without the quencher plus kqq, right? So again, this form, you're just measuring the lifetime of your system and not necessarily fluorescence yield and such, right? So it's a little bit less experiments you gotta do to do this, okay? But you still need to know what I should say, and in this case, you don't need to know what tau naught is, right? If you're just interested in kq, well, kq is now the slope, right? Plotting 1 over tau naught versus q, that slope is just going to give you kq, right? And then the y-intercept will give you tau naught, right? So this is a way to get the lifetime without the quencher and the quenching constant in one plot, right? And so this is, again, this is the Stern-Volmer equations, right? With these quenchers, it's used very often in chemistry to study excited states of molecules and things like that, and you can do a lot of interesting things with this if you have some ideas of how this quenching rate constant works and things of that nature, okay? And so that does it for this video on photochemistry. It was a little bit of a longer video, right? But we covered a lot here talking about kind of what is photochemistry, and some of the general concepts and ideas behind photochemistry and the kinetics within photochemistry.